Hello everyone, and welcome back to the stream. In this stream we're going to be building a falling sand game in Bevy using Rust. Okay, so we're just going to get straight on into it. Last time, you may remember, we were building the pipeline. So this was for basically the custom render pipeline for Bevy. And we started to write the shaders, just placeholder compute shaders that we're going to end up using. And we integrated those into our engine, into Bevy. We had an extract resource plugin using the cellular automata image, and yeah, basically created a setup function and added that as a startup system as well for when the game begins. And the first thing I want to do is refactor this a bit. So I put all this in main, but I think it would make a lot more sense for it to go into lib, because this is our own custom plugin, right? That we're calling game plugin, and really we want all of our stuff to go in here rather than chucking it in main, because main is basically a separate binary. That's why I had to end up doing this strange, import stuff to get it to work. Really, I just want to import the game plugin and use that directly, rather than having to faff around importing cellular automata image and other stuff that should really remain internal to what we're actually doing. So I'm going to move this stuff from main. Set window icon is fine in main still, but the setup function I'm going to move from main. I'm going to put that in lib instead, where our own plugin is. Okay, so I'm just going to put it there in front of display FPS, and we're going to add this as a startup system. So much like we've got main here, so we did have set up here as our startup system. Just going to remove it and add it in lib instead. I might as well put it here. Makes sense, doesn't it? Add startup system, and then that's set up. So let's just check that everything's okay there. We'll just build it. Should all be alright, hopefully. Yeah. Just getting the warning about init update and text bind group layout not being used, but that's cool. Falling sand game, cellular automata image not used. Okay, that's good. So, because that was in our setup function, we were calling create image. So we can now remove that import. Hopefully we can remove both of those, like so. It's tidying things up quite a bit. Yeah, so now we have this final plugin, the extract resource plugin, that enables our cellular automata image to be extracted as a resource for Bevy to use. We can just remove that from main and put that one in lib as well. Let's just put that. Now, was that in the render app? No, it was just literally a plugin, wasn't it? So app. Put it there. Hopefully that should be alright. And then we want to be able to basically import that. Okay. So that's good. We're using it in more internally now. We can import that as well. It's all good. And I will just tidy up our imports a bit, because this is a bit messy. So I want Bevy to come before our own crate stuff, I guess. Still a bit of a noob when it comes to doing Rust libraries and stuff, but all the Bevy stuff first and then all the crate stuff seems to kind of make sense to me. Right. So let's check if that builds. Hopefully it'll be alright. Okay. And then we can get rid of the extract resource plugin import from main as well, because we're not using that now. Looks much more clean now. So now we've got main. It's just literally importing our plugin, and then we're going to actually add the plugin which then in turn will call all of our internal stuff inside build for our plugin, where we add our other plugins. So that is great. I'll just compile one more time just to check everything is good. Okay. Alright, great, and we'll run and make sure we don't get any untoward errors or anything at runtime. And that's all looking pretty good to me. Okay, excellent. So let's commit that while we are at a convenient point. Let's add our changes and then write a commit message that just says refactor plugin init I'm not going to put refactor, I'm just going to literally put move plugin init code from main to lib. That'll do us. Alright, great. Okay, now we can carry on with where we got to before. So we've got a placeholder compute functions, compute shaders I should say, but we're not using them yet. Alright. And we have in it this is a resource, haven't we? Is that right? We got our pipeline. Yeah, so we've currently got the render app, which is a sub app of the main app, and then we're initializing our pipeline as a resource. Okay. So moving on from here, we are now going to actually build the bind group. And this is a collection of resources. A bind group, that is a collection of resources. It can be buffers, textures, and samplers. They're bound together and are made available to the shaders during rendering. Okay, so the bind groups are created by the application and then bound to a specific pipeline layout, and that defines the expected bindings for the resources in the group. Okay, so we are going to create a bind group for each render instance. So let's do this in pipeline. Okay. So we're going to create a struct. It's called cellular automata bind group, and then this is going to it's just a shorthand to a bind group basically. This struct with basically one field. Is it called a unit struct or something like this? Basically just creates an alias. So cellular automata bind group is a bind group. So that's good. Now we're going to create a function, qBind group. We're going to have a fair few parameters for this. So we've got commands. The render device, which is a resource of type render device. And we're going to have our pipeline, which is a resource of type cellular automata pipeline. We've got GPU images, which is a resource of type render assets. Which itself is of type image. And then what do we want to call this? This is our image. We want to call it the cellular cellular automata image, and that is a resource of type cellular automata image. Spoiler alert. Okay. And then we're going to use our render device. Okay, let's get the view first. So from the GPU images, we want the game of life image. No, cellular automata image, ours is called. So that gets us the view that we're interested in. Remember, these are handles as well, so we can kind of treat them like pointers. Basically, they must have the indirection implemented, so we can just use this sort of reference syntax to be able to treat them as if they were pointers, even though they are technically handles, which is more of an ID, a unique ID to a resource. But for all intents and purposes, we can treat them the same. Right, so now let's actually go ahead and create our bind group. So we want to use our render device to do this, and we probably actually want to import some things here. Because our autocomplete's not working, so let's just get rid of that for now and actually import some stuff. Hopefully those are all making sense. So we got image from the prelude, res from the prelude, and then render device comes from Bevy renderer. Okay, so that should help somewhat. Let's get that back. Not that. What were we doing? We were creating our bind group. We were going to use our render device. Here we go. Create bind group. So that's good. And for this, we need a bind group descriptor. Fill in the missing arguments. So we've got a bind group descriptor, and now we should be able to fill in the missing fields. Label, we are just going to give it a sensible name. Cellular automata bind group. The layout, we are going to use our pipeline, because that already gives us our texture bind group layout. And then our entries. Can we fill this in? No. Okay, so this is a bind group entry. At binding 0. And what are we going to bind? We're going to bind our binding resource, not a sampler, a texture view. And that is our view texture view. All right. Let's finish that statement that creates the bind group. And now we're going to insert this resource. Game of life. Not game of life, cellular automata bind group. Right, so that's just wrapping it in that helper type that we created up there. Okay. And now we can actually add this system to our render app. So the system is called QBindGroup. Remember, a system is just a function as far as Bevy is concerned. And let's go back to lib. Hopefully we won't need to touch main, so I'm just going to shut a few of these windows down so that we can have a bit more clarity. Okay, image we're probably okay with for now. So there's our pipeline. And now let's add the system to our render app. So we init the resource. Now we can add system pipeline queue bind group, and then put it in the render set queue. Alright, and the reason to add it to the render set queue, creates bind groups that depend on prepare data, and then it queues up the draw calls to run during the render step. Okay. And now if we run, we should get an error. Okay. The trait resource is not implemented for cellular automata bind group. I think I have forgotten a derive statement somewhere along the line. Yes, can just derive resource for our struct. Oops, don't want a snipping tool. Good old Windows hotkeys. Okay. So we just want to derive resource here, so that we can treat that like a resource. Let's try running again. Okay, looking a bit better this time. Alright, and we're running. We have an error. No sign of an error. Okay, fair enough. Yeah, we definitely added it as a system in the render app. Okay, bit strange. I was expecting an error there. Not to worry, we'll plow on. Okay. Right, so now we're going to move on to nodes and the render graph. So how Bevy implements the custom rendering stuff is very similar in an from an implementation point of view to how WGPU does it. So by learning this, you're going to become pretty familiar with the mechanics of WGPU, which is always a good thing. And we can have a look at the render graph resource. So I just get the actual string up somewhere. So find it. just import it. Got it. Okay, so the render graph configures the modular, parallel and reusable render logic. It's a retained and stateless. It is retained and stateless structure, which cannot be modified while it is executed by the graph runner. Right? Nodes, it says nodes themselves may have their own internal state though. The render graph runner is responsible for executing the entire graph each frame. It consists of three main components: nodes, edges, and slots. Nodes are responsible for generating draw calls and operating on input and output slots. Edges specify the order of execution for nodes and connect input and output slots together. And slots describe the render resources created or used by the nodes. So hopefully that makes sense. And also it says additionally a render graph can contain multiple subgraphs which are run by the corresponding nodes. And every render graph can have its own optional input node. And then it gives us a little example there. Okay. Just creating a simple input output and connecting them together with an edge. So that all sounds good, right? So at the moment we only have a single pipeline, so we'll only need a single node, and our node is going to have a state for processing for determining which stage the shader is currently in. Remember we had the loading, init, and update states. So it's I'm just going to get rid of that reference there. And we'll switch back to pipeline. And we can add on node. Okay, so let's create a little bit of state before. It's going to have those three different states that we've got. The loading state, the init state, and the update state. Very simple, very familiar if you're familiar with other game engines. Now we're going to create a structure that is going to represent the node, cellular automata node, and it's going to contain our state. Single field, that's that. And then we want to just implement default so we can have the starting state as something sensible. Come on, autocomplete, keep up. And this is going to be, can I just autocomplete that? Give me default. Implement members. Yes. Cool. That's what I wanted. And then you're just going to basically create ourselves with the state set to, guess what? Cellular automata state loading. Because we start as that state. Okay. Now we can add the node to our render app. And we'll do that in our plugin. So there we go, we've got the render app here. So first thing we need to get the render graph, which we need a mutable reference to because we're going to change it. And we get that using the render app world resource mutable render graph. Oh, yeah, and it's a generic type. Bit of a pain. Right. So that should get us the render graph. And now we can use that to do as per the example we saw in the documentation. So we're going to add a node. Can we see the docs for that? What parameters do we need? So we need a name and a node. So the name can be cellular automata graph. And then we can add our node. With default params. Yeah, it's going to complain that that's not imported. No. Oh, do we need... Yeah, I did. Oh, enter. Yeah, import. Come on. Gosh, it's... C-line is rather slow. Oh, enter. Don't want to qualify path. Want to import. Alright, we'll just do it the old-fashioned way. Oh, yeah, it's imported it. Just hasn't picked it up yet. There we go, finally. Goodness me. That is rather slow. Okay. So, we've added the node. Now we want to add the edge. So, again, we'll use the render graph. Add node edge. Node label. Yeah, I'm just going to rename this one cellular automata. It's calling a node a graph is not very helpful. And then we want this to run our node before the camera driver. All right? Because we want to render before, we want this to render in the background before we render to the screen, to the camera. So we get in the main graph. The camera driver. All right. I'll split that onto 2 lines. It's just a hair over what I'm happy with. Okie dokie. Right. And obviously our node starts in the loading state because we're using our default implementation. Now we need to have to implement node for this. Probably can we get a runtime error? Or yeah, probably a compilation error. Let's have a look. Because although we've called this a node, we haven't actually. Where is it? Yeah, so there we go. So we haven't actually implemented the trait for cellular automata node. So let's go ahead and do that now. And we can specify it like this because node is kind of a generic name, isn't it? It makes it a bit clearer. Right, so that's what our trait is going to be. Import the render graph. Give it a second to tick over. Let's just check it definitely imported. Yeah, you've got it. Okay. And now, right, so we can actually have a look at a render node that can be added to a render graph. And we can just hit implement members. Alright. Will that implement all of them? Just run. We want to implement all of them. Alt, Shift and Enter. Is there a way to select all? Okay, we'll do it that way. Input, output, update and run. Okay. So the input defines required input slots, output defines produced output slots. And we don't really care about those. For the moment. But we do care about update and run. Alright. So let's focus on run to begin with. So I just want to put the parameters in a tidy way. So we can see what's going on a bit better. World, and then the result is here. So we just need to return a result to implement this as a bare minimum. So we'll just return OK for now. Alright. I don't think we need these. Let's just delete them for now. Let's do update. So we want to check if the pipeline is loaded and transition to the next stage if it has. So let's do that. So let's get the pipeline first. Pipeline. Yeah, good. And then the pipeline cache. It's got an underscore. I'm not really a big fan of that. Oh no, this is just pipeline cache. So we'll get that. Pipeline cache. Have we imported that already? Yeah, maybe we have. Okay. set pipeline cache, world resource pipeline cache. Okay. Thought we had an error. I think it was just a phantom error. And now let's match on our state. Figure out what we're going to do based on what state we're in. I want to be able to autocomplete. Yeah, add our patterns. Jolly good. So if we're in loading, we want to check if we've got a cache pipeline state from in the pipeline cache. And if we have, transition to the init state. If we are in the init state, we'll do a very similar thing and check if check for the update pipeline instead here to see if that's loaded, and then transition to the update state. So a bit of boilerplate really, just to handle this lifecycle stuff. And then update we'll just leave for now. Okay. Normally if you need to recreate your pipeline or rerun the init pipeline, you might do that here by changing the state. But now let's get to the meat of it, and that's the run function. So this is where we'll actually be running our compute shaders. But first we need to set up the init pipeline. So let's get our texture bind group. Cellular automata bind group there. First member of, which is the bind group itself. And then we'll get the pipeline cache as before. And our pipeline as well as before. That's world resource. So get a resource. Cellular automata pipeline. All right. This should be image bind group. My mistake. Because we're going to use this to queue each frame to be used by the shader. Okay. Now we actually begin the pass, compute pass. So let's use the render context. Command encoder, begin compute pass. Just with the default compute pass descriptor. And now we actually need to assign our bind group to the pass. So pass set bind group to do that. Yeah, great. At the first index, our cellular automata image bind group goes there. And then offsets we don't need to worry about. Alright. And now we're going to use our node state to see which pipeline to execute. So we'll do a match on the self.state, fill in the values, the patterns. So if we are either update or loading, we're going to handle those the same and do nothing for now. But in initialize, we're going to get the init pipeline. From the pipeline cache, get compute pipeline. And then set our pipeline in this pass to that init pipeline. And then actually tell it to execute. Dispatch work groups. And now we need to know our simulation size here, which I don't think I've defined anywhere. But it's probably a good idea to do that. So yeah, let's put some constants in lib. Simulation size, which is going to be basically the grid that we're going to use to do the cellular automata. And we will do 1280 by 720 for now. We probably want to do this based on resolution if we're going to be running full screen, but let's just hard code it to some constant values for now, just to get us going. And then our work group size, again, we probably want to be able to determine this by some kind of means at runtime, just so we can detect what platform we're on and maybe use something that's optimized. But for now, we'll just set it to 8. Okay. Now, actually, in our setup, we can use the simulation size, because I think, didn't I set? Oh yeah, I set 800 by 600 to our image width and height. But now we actually want to use sim size for this. simulation size, width and height. Okay. Alright. So now we're using those there. That's all good. And we can come back to where we need to use them here. So back in the pipeline. Alright, sorry, back. Are we in the pipe? Oh, we're doing the node, aren't we? So yeah, when we dispatch the work groups now, we have these values available to us because we've defined them as constants. So we can use them to calculate what we need. Simulation size. This is basically width. Let's import. So that's width, and the height. It's just going to use the second of the tuple, and then Z is 1. Okay. I want to import work group size as well. Come on. We will come back to the update pipeline as well. I'm sure this is just very slow here. Come on. Yeah, we've got simulation and work group size. Just going to build that. See where we are. Okay, so it's saying it's not finding our image bind group. Did we call it something else? We probably did. Oh yeah, we just got our cellular automata bind group. Let's rename that now then. Could do it automatically, but it's quite nice to do it. Manually sometimes, just so you get a chance to review the code and make sure you're happy with everything. Alright, so let's rebuild. Probably have some errors as well because we've got a bunch of unimplemented things, haven't we? Okay. Just telling us we haven't used the graph. That's alright. It is going rather slow, isn't it? Okay, done. Cargo build says it's still running here, but it looks like it's finished on the right hand side. Okay, let's press on. So yeah, if you're wondering what a work group is, it's quite a nice visual representation that I will grab for you. So here are the work groups, and then inside the work groups are the workers. So you can see the work group size. We defined it in our shader as 8 by 8 by 1, I believe. Yeah, here we go. 8 by 8 by 1. And you can also think of this as, you can think of a compute shader as a function that's run as a bunch of nested for loops, but each loop gets executed in parallel. Right. So all of these are in parallel, and all of the workers are also in parallel, all at the same time. Right. I think we can run now, and we should still have our lovely black screen, but hopefully no errors. Okay. Didn't see any errors. I think we're good. Yep. All right. So that's all looking quite good. Now we can actually move on to writing our shaders. And we can start with our init function. All right. And we can see the function inputs in this. Let's actually start here. So we've got a built-in value for the invocation ID, right, which is essentially its position in the compute shader grid. And we can actually find our location by using that. So we can define a variable location, 2D vector, type 32-bit int, and use the invocation ID xy. This is giving us the x and y values as one value, essentially. Swizzling, that's called. Okay. So we essentially want to randomize, just so we can visualize something, we can draw some random numbers. But I want to not do that quite yet. I just want to set everything to white to begin with. Right. So let's do that with a texture store function. Our texture, which I believe is in our in our bindings here in bits. So let's use our texture and our location, and then we'll just do we'll create a color. Right. Of 32-bit floats. It's gonna be can we do that? Can we just use one? Let's see. So one being white, essentially, right? Do I need? I'm not sure if I need to cast that number as well. Well, I guess we'll find out. So this will compile. Sadly, compile at runtime, so we won't know till we run it if our shader is okay or not. Let's have a look. If it works, we'll get a white screen. No. So expected a comma. Oh yeah, of course, we actually need to use it. And put a semicolon on the end of that statement. Let's try and rerun. So there we go, a white screen. Excellent. So that shows that our initialize function is working, and we're able to set this color in the compute shader. That is very inefficiently setting it for every single pixel, for every single frame, but at least we're able to draw something. So that's very cool. If we wanted to set it to something else, red, green, blue, alpha, will essentially achieve the same thing, but if we just want blue, for example, set red and green to zeros, and that should, in theory, give us blue. So let's try that one. So while it loads up there, and we do indeed have blue. So you can see we're now able to control the color of each individual pixel and do it that way. Let's just try and say if location is greater than 300, if location X is greater than 300, okay, that was actually quite a useful error there. Look, expected paren left, so that tells me that if actually requires a statement to be in parentheses. I'm not massively familiar with WGSL, so I'm not sure if I can do this and it will be happy or not, but let's find out. So if it's greater than 300, I'm going to set it to blue. Otherwise, I'm going to set it to, I'm just going to copy and paste this. Otherwise, I'm going to set it to green. Red, green. The second value, and I'm not a massive fan of these very harsh colors, so I'm just gonna do it slightly better than that, bring in some of the others, so this will be sort of a slightly muted green, And the same with this, just make it a slightly muted blue. Slightly more of a pastel, slightly easier on the eyes. So if it's greater than 300 X, let's make that 500. So if X is greater than 500, we're going to draw sort of a palish blue. Otherwise, we're going to draw a palish green. So we're actually doing some computation here. So let's see if it works. Just to prove that we can actually do some computing in our compute shaders. Okay. And sure enough, we've got a compiler error. Oh, right, okay. Where is this? Ah, yeah, right. So it's expecting us to actually set something for the initial value of color. So let's try and set it as something and then mutate it. I could always look at the WGSL documentation, but I quite like to just tinker around and see what happens. So let's have a look, see if this works, see if we can actually mutate a let, which you probably can't. Nope, cannot assign because, yeah, it's immutable. Ah, consider declaring it with var instead of let. Great. Alright, so how about we just define it as green, just as to be a bit tidier, and then we won't need the else branch of the condition. We can just set it to blue if it's greater than 500 on the x, in the x coordinates. Okay. Drum roll. Yay! There we go. So you can now see pixels that have their x coordinate less than 500 are set to this pale green color. Pixels that are greater than that are set to this pale blue color. So there we go. Isn't that wonderful? We're actually computing in a compute shader, and we're doing it at well over 260, 250 frames a second or so. So yes, very happy about that. Okay, great. Right, let's commit that. And I think that will be us done for today. Add our changes. And then we will say implement initial init compute shader. Okay, all good. Right, thanks for watching. Tune in next time when we'll actually add a bit more logic and do the update function. And yeah, this is quite exciting. We've actually got something rendering to the screen. I'm pretty happy about that. So yeah, thanks for sticking with us for this time. I know that it took a while to get all of this boilerplate set up in terms of the pipelines and the nodes and everything. But, you know, always nice to see something rendering on the screen. Now we actually have all that set up. And now we can get on to the fun stuff, really. Okay. So, yeah, once again, thanks for tuning in. And see you all next time.